practicals. But I thought you might want a little bit more detail on post-processing operations that you can use in the post-processing language, to some of the more complex things that you can do to transform the n-dimensional array data structures that you have. So I'll go through maybe about half an hour discussing some of that, which hopefully give you a bit more insight into what the existing protocols on the Web Lab are doing. And if you want to adapt and do different post-processing, gives you a starting point. And of course, Gary and Aidan and I are around if you get stuck and have questions. So I'm calling this the sort of the post-processing bit of the language because that's mostly where it's used, but it comes up elsewhere as well. It's primarily for performing mathematical operations on n-dimensional arrays and just general mathematics on numbers as well. And these expressions come up in various places. So protocol inputs have default values that can be defined by arbitrary expressions. They can be arrays. The library section, with often defining functions for use in post-processing. If you're defining ranges, a vector range, you can define a vector with arbitrary complex expression there. Similarly, the while ranges, that condition can be an arbitrary expression. And also for setting model variables to particular values within modifiers as simulations are running, you can put arbitrary expressions in there. So these expressions crop up in different places, not just in the post-processing. Now, I've talked about expressions, it's just a mathematical expression that computes some value, and typically that will either be a single number or an n-dimensional array. And there's also statements, the main component, that just sequence operations. So usually these are assignment statements. You're just assigning some expression, it's evaluated and stored as a variable. But you can also define functions for use, and there are assertions in the language as well for checking that you're getting the inputs that you're expecting, so that you can have some safety checks in the functions that you define usually. So there are various operations on the language, and I'll go through and try and explain how each of those work. But there's also all the just general arithmetic operations that you would expect, plus, minus, times, divide, relational operators, and so on, that's in the language, and just fairly straightforward and intuitive. The array operations, not necessarily so intuitive in some cases, unless you're familiar with functional programming, in which case this will seem like old hat. But I don't think that applies to many of you. So creating new arrays, the easy case, in the case that's probably most familiar, is just to list the elements, 3, 5. That is a one-dimensional array with 3 elements. And we can create large arrays in exactly the same fashion. So I can stick another one in there. Now I've got a 2-dimensional array that has 2 in the first dimension and then 3 in the second dimension, 2 by 3 array. You can also create arrays by comprehensions. So rather than listing every element explicitly, you can actually compute the elements by some expression. So you can write something like I times 2. So here's an expression defining each element of the array. And then I'm saying a sort of kind of a loop to say I in some range, 1 step every second up to 7. So this is a bit like a uniform range expression in simulations. We're saying I is varying from 1 up to 7 in steps of 2. And for each value of I, we're going to compute this expression and use that as the next element of the array. The one thing to watch out for is that these ranges are Python-style ranges, so you don't actually the end point. It's closed at the start and open at the end, which is a bit of a gotcha until you're used to it. So I here is going to go 1, 3, 5, but not 7. And so the array as a whole is then just going to be 2, 6, 10. So that's comprehensions. And those are the 2 ways of creating new arrays. And you can stick any expression in here. This expression could actually create you an array itself. And then you have an array where every entry is an array, so you're adding an extra dimension on. You can build up quite complicated arrays if you need to. The other way is, if you've got an array, you want to look at just a portion of it, taking a view or a subarray. And this is, again, inspired by Python syntax. So if we have an array A, say, square brackets indexing, we can just sort of take a single value out of the array. So it's a one-dimensional vector. This takes the second entry. All indices start at 0, as in most programming languages, except MATLAB. We can also take a subarray. So we can take, say, from 1 up to 3. And again, this is half-open Python-style indexing. So if we have our array is 1, 2, 3, 4, 5, and we take 1 up to 3, we get, starting from the second entry, 2, we're going to get the next one. We're not going to do any. Those of you familiar with doing good programming in Python, this will seem very natural. For those of you not, it would probably take a little bit of getting used to. The reason for doing it very nice once you start doing negative steps, so you can actually put step values in here and sort of take every second, for instance, but equally you can go backwards. So I can say I'm going to start from the end of the array, count backwards and go to the beginning, and that's just a quick way of reversing the array. And once you start doing negative steps, the half-open semantics work much more nicely doing that kind of thing. So that's subarrays, and there are various examples in the documentation for playing around and seeing how it works in different scenarios. The third kind of operation is a map, and this is for applying a function to every element of an array or to every element of corresponding arrays. So you can sort of take the element-wise difference of two arrays or sums or that kind of thing, but you can map an arbitrary function onto a collection of arrays. So the general syntax, if we say map, and then some function onto arrays, and here, because we've got two arrays that we're mapping this function onto, we're expecting this to be a function that's going to take two arguments that are numbers and return me a number. And so for every corresponding element of A and B, we apply the function to those two numbers, and the result forms the corresponding entry of the result array. So let's take an example, might make that a bit clearer. And I'm going to map, in this case, a one argument function. And I'm going to demonstrate also some shortcut syntax that's often used for maps. So here I've got an operator minus that takes the unary minus of a number. And I want to just change this into a function that takes one argument and returns me the negative of that. So I can use this @ symbol to say I've got a one argument operator that I want to turn into a one argument function so that I can pass it to map. And I'm going to map that onto an array 1, 2, 3. And that's going to give me also an array of exactly the same shape, but each entry is negative. And you can do exactly the same thing with two argument operators. So say we could take two arguments for a plus and give it arrays 1, 2, 3, 4. And now we're doing the element-wise addition of these two arrays. We've got 4, 6 as the result. And that comes up quite a lot in most of the protocols, I think, if not all of them have some maps somewhere in there. Another operation that, again, is familiar to functional programming background people is fold, sometimes also called reduce. And this is basically collapsing an array along a dimension. So this is very useful to finding things like maximum, minimum, sums, or products, where you want to take, say, a vector and find the maximum value, or multiply all the elements together and take the product over a vector. And that extends to arrays as well, where you just choose sort of which dimension you're collapsing along. You've got a two-dimensional vector, you might collapse it in that direction or in that direction to get down to something that's one-dimensional. Again, this one is much easier to demonstrate with a few examples. So if we take, say, the sum function for taking the sum along some dimension of an array, and we could define sum of an array A in terms of fold. So that's going to be folding the addition function because we're wanting to sum things. And always with a fold, you want a binary function that takes two numbers. It's going to add things together. We're going to apply that to the array A. And we also typically give an initial value that if you had an empty vector, which you can't actually have in this language, or if you just had a one-element vector, you would want to say something plus that one element. And the natural initial start for a sum is 0. So if we have just a one-element vector, we get 0 plus that number, gives you the sum that you'd expect. So if we take then an example of how that works, sum up the vector 1, 2, 3. Effectively, what that is doing is get the right round, doing 0 plus 1, taking the result of that, adding on 2, taking the result of that, adding on 3, and then sticking that back in an array of the same shape. So you get out as your result just a one-element array with the value 6 in it. So the result of a fold always has the same number of dimensions as your input, but the length of the dimension you're folding on ends up being 1. It's just compressed down from 3 entries, pushed down to 1 entry along that direction. And again, there are quite a few more examples in the reference manual you can have a look at to get a feel for how this works in different cases. Basically, you're collapsing an array down in one dimension, and most of the time you'll be using the built-in functions for doing maths and sums and that kind of thing. And then the final pair of operations are for finding interesting parts of an array. So there's a find operation that gives you the indices where an array is non-zero, and the corresponding index operation that just gives you a subarray containing those portions. And often that's used in conjunction with map to say, rather than just finding where an array is non-zero, I want to find places where an array satisfies some predicate. So I can map a predicate function onto the array to get an array that's just 1 where the predicate is satisfied, 0 elsewhere, then apply a find to get the indices where that happens, and then an index to extract just those entries from the array. And that kind of sequence comes up quite a lot. So again, a couple of examples to illustrate. If we take, say, just applying find directly onto a vector, in this case it's going to be 5, 4, 0, 1, minus 1, 0. And what I'm going to get is a two-dimensional array giving me the indices where this thing is non-zero. So the length of my first dimension is just the number of entries. In this case, there are 2 of them. And then for each one, I get a little array which gives me the indices. In this case, my input is one-dimensional. So each indice just has one value in, turning me along that direction. So I've got 0, 1, 2 is the first, non-zero, it's not zeros. So the first one is at 0. Second one is at 1. 2 is 0, so we're skipping that. Next one 0 is at 3. Next one 0 is at 4. And then 0 at the end gets skipped. The index operation has a squiggly bracket syntax. So if we've got some array, rather than this being a function, actually has a special syntax in the language. Rather than the square brackets for indexing with regular subarrays, it has the squiggly brackets, and you pass it in an array that's the result of a find call, typically, that tells you the indices. But because the language requires you to have regular arrays, and often if you're indexing, you're not going to get something regular, there are various other optional arguments that you can put in here to say how we take something that's irregular and make it regular again. So if, say, I had my input array being this two-dimensional array, 5, 6, 7, 9, 10, 11, 12, 13, 14. So I've got here a 2D array, and I can make that into proper syntax by putting in some commas and square brackets. If I say, take just the odd entries of this array, what I would get out at the end is 1, 3, 5, 7, 9, 11, 13. And that's not a regular array anymore, so that's not allowed. And I'm going to get an error if I just try and index with those positions. So I've got to decide how I make this mess into something that's regular, either 2 by 3 or so I can either make it regular by saying I'm going to add some extra values. So I'm just going to put, say, some zeros. Line this up. I'm going to put some zeros in where I've got extra thing, not enough entries. So I can say 11, 13, put some zeros. Or I can throw things away to make it regular. So I could, instead of adding extra zeros on, I could say throw away the 9 and make it regular in that way. Or I could throw away from the other direction, throw away the 5, make it regular in that way. And I could also throw away vertically, throw away entries. In this case, you end up with roughly the same thing. So the extra options that you can apply in this indexing operation basically say how you're going to do that. So you can pass in which dimension you're going to either contract it or expand it along. And you can say whether you're going to add new values, which is called padding. And you can say whether you're padding on the right hand, the end of that dimension, or the start of the dimension, and what value you're padding with. Or if you want to throw things away instead, you can shrink the array, and you just say direction of 1 or -1, depending on whether you're shrinking at the end of the dimension or the beginning, you're throwing things away. So if I put that all together, call this my array A, and I want to find the odd entries. So that would be A, curly brackets. I've got to find here to work out the indices. I want to find the odd things, so I've got to map a predicate that gives me odd numbers. Finding odd numbers, I'm putting in here an anonymous function, just defined using the lambda keyword. This is a function that takes one argument. I'm going to call x, and for every element x in this array, I'm going to take the remainder with the mathml rem operator of x divided by 2, and I'm going to say this is going to be 1 for odd numbers, 0 for even numbers, so that's giving me 1 or 0 where I want. So that's great, that's the predicate function I need, and I can map that onto my array A, close the map, close the find, and then I need to say how I'm going to shrink or pad. And if I say that I'm going to shrink along dimension 1, which is the inner dimension here, say shrink 1, and that gives me actually this version of the output. So I'm shrinking off the end of the inner dimension, and that's the regular output that I get. If I said shrink -1, I'd get 7, 9 instead. And similarly, if I'd said add at the end with zeros, I would get one I showed earlier, 5, 7, 9, and adding the other ones with zeros. So you can play around quite a bit to get different ways of making an array regular. For the most part, you probably won't needing to write things like this. They're buried within some of the standard libraries, but sometimes you'll be doing things that aren't already implemented, and then it gets more complicated if you start thinking about how to manipulate arrays in detail. Just a few other miscellaneous features from the language before I talk you through a bit about what's in the standard libraries. We've got accessor operations, where you can just have a variable and then dot is array, for instance, to check whether it's an array, similarly for if it's a simple number. You can also, where you do have an array, extract the shape of that array or the number of dimensions, the number of elements, so that you can, say, take the array shape and treat that as an array itself and do operations on that. When you're defining functions, you can actually provide default values for arguments. So I can define a function f and an argument a that I can say defaults to 0. And then when I call that array, when I call that function f, I don't necessarily need to pass the value for a. I could just say f by itself, and the default will be used. If you've got a multiple argument function, actually you can explicitly say for this parameter here, I want to just use whatever the default was, which is particularly useful if you've got, say, something like this. 2 parameters both with defaults, and I want to use the default for A and then pass something different for B. I can do that. So you don't need to know about what the defaults are for earlier values if you just want to supply a later one. We've got tuples, so pairs, triples, and so on that you can do. So that's particularly useful for returning values from a function. If you want to return 2 things, you can just return a pair. And when you're then reading that, you can actually say a comma b is equal to f 2, 1. So you can unpack the pair that's returned into 2 separate variables if you want to. And then there's a few bits that just try to make it a bit easier to write protocols using this language if things go wrong, as they often do as you're trying to get something working, even for me. The error messages try to give you information about where in your protocol the error has arisen, what values of variables were at that point, so you can figure out why is this operation not doing what I expected it to. And you can also trace particular values, so you can stick a question mark on the end of any variable in any expression, and you'll get output a synopsis of that variable, and in a separate trace.txt file, you'll get the full value of that variable output as the post-processing goes through, which gives you another way of figuring out what's happening exactly in your post-processing operations to figure out what you should be doing to get the results that you want. But there are plenty of operations defined for you, so a lot of things you might want to do, hopefully, is just a matter of doing a function call with appropriate arguments, and you don't need to get into the gritty details of the language. So you'll notice a lot of protocols are importing things, one called basic library, one called cardiac library, and this is a list of all the functions defined in those. So in the basic library, we've got sort of generic operations on arrays, I guess. Things like max, min, sum, product, the mean value of an array to compute. And all of these operate along one dimension of an array. In fact, you can think of it like if you've got a 2-dimensional array, this has multiple copies of, or multiple one-dimensional vectors inside it. So with any n-dimensional array, you can think of it as having lots and lots of one-dimensional vectors arranged. And when you're doing these operations, they operate over all the vectors that you've got simultaneously. So you're just deciding, when you're deciding which dimension to operate over, which way are my vectors aligned in this multi-dimensional array, and I'm going to operate over all the vectors in this simultaneously. So I'm going to take the maximum along each vector, and I have a 2-dimensional array, take the maximum in one direction, I get a 1D column vector, take the maximum in the other direction, I get a 1D row vector with my results. And pretty much all of these similar ways. They can operate over a multidimensional array, but you can think of that as basically you're doing the same thing over lots of 1D vectors just simultaneously. There's diff and grad, useful for working out the gradients if you've got x and y values represented in your two arguments. Permute is mainly useful for doing sorting, so you can sort arrays along a particular dimension either just by the values in the array or by some other vector that gives you the sorting key. Join sticks two arrays together. Two arrays, stick them together, you get a bigger array. You can also stretch arrays. So if you've got an array that has length 1 in some dimension, you can just stretch it out and produce multiple copies. So if, say, I've got an array, a 2D array that just has length 1 in the first dimension, I can call stretch on that, and I can get multiple copies of that vector. However many I ask for. So useful for replicating an array before performing some other operation on each copy. Shift is a sliding sort of operation. So if I've got a vector, say 1, 2, 3, 4, 5, I can call shift to shift it either left or right, and I get something that's the same length, but the values have shifted along. So if I shift it right, say, by 2 places, I get 1, 2, 3, and I filled in just with the initial value at that side. You can shift in the opposite direction as well. Window and localize work together to basically perform an operation rather than, say, taking the maximum along a whole vector. You can actually take the maximum just within a particular window. So you can say take the maximum value within the 5 values centered around this point. So you get a vector that's the same length as your input, but each entry of that is the maximum within the 5 entries centered on that point. And these sorts of things are mainly useful rather than a standalone for building up bigger operations. They were all actually added so that I could do action potential duration calculations. All of these operations are needed to do that, including this one, interpolation, which does linear interpolation along a particular dimension of an input array, so that you can search for target Y values. If you've got some X data and Y data in arrays, you can linear interpolate the X data to get Y values more precisely. So that gives us APD to a better resolution than the typically 1 millisecond output data. After is useful for finding parts of an array that occur after a particular time. If you've got one array representing time, one array representing values, you can just take the subarray after a certain time, but it doesn't necessarily have to be time. Count just counts the number of entries that satisfy a predicate. Filter gives you only the entries satisfying the predicate. Transpose is the transpose of a 2D array. And then these are more sort of utility type operations for building and evaluating arrays. With all of these, we go to the file itself in the browser. You can look and see this is defined using the post-processing language. Let's see better if the font size is a bit bigger. So all of these functions are just defined by expressions in the post-processing language, and they're all commented with explanations of what they're doing, the parameters, default values, and so on, so you can have a look and see. For a lot of the more complicated ones, there's examples of use as well, and the reference manual often has links to further examples, and in particular test cases in the automatic test suite for the software. It checks that these examples do still do what I claim they do when I change them. You can have a look through that for more details about any of the functions. Similarly, you can have a look at the Cardiac library for more details about the functions computing action potential duration, diastolic intervals. The equivalent concepts works on calcium transients as well. those are quite fun to look at if you want to get an idea of what is possible. They took me quite a while to write. APD is quite complicated. So as I say, there is a full reference manual for the protocol language on the wiki function curation system. Often actually looking at the comments in existing protocols and libraries is the best place to start. Find something that does almost what you want and figure out how it works and adapt it. But there is a reference manual for describing exactly what syntax is allowed, what the operations do, about how things work. So that's it. Any questions? Have some fun writing more protocols.